The old quantum theory emerged in the early 20th century to explain phenomena that classical physics could not account for. This theory, though ultimately incomplete, was essential in bridging the gap between classical mechanics and modern quantum mechanics. One of the driving forces behind the development of the old quantum theory was the need to explain blackbody radiation. Classical physics predicted that the energy emitted by a blackbody should increase indefinitely with frequency, a result known as the ultraviolet catastrophe. The old quantum theory addressed this by introducing the idea of quantization, the notion that energy is not continuous but comes in discrete packets called quanta. This concept revolutionized physics, providing a new framework for understanding atomic and subatomic processes. Despite its successes, the old quantum theory had significant limitations. It struggled to explain the spectra of more complex atoms and could not account for the fine structure of spectral lines. Nonetheless, it laid the groundwork for the quantum mechanics that we know today, marking a pivotal moment in the history of physics.
Max Planck is often credited with the birth of quantum theory. In 1900, while studying blackbody radiation, he proposed that energy is quantized. Planck introduced the idea that electromagnetic energy could only be emitted or absorbed in discrete units called quanta.
Planck's hypothesis was that the energy of these quanta is proportional to the frequency of the radiation. This simple yet profound equation marked the beginning of quantum theory. Planck's work successfully explained the observed spectrum of blackbody radiation, resolving the ultraviolet catastrophe predicted by classical physics.
Planck's groundbreaking work earned him the Nobel Prize in Physics in 1918. His introduction of energy quantization laid the foundational stone for quantum theory, influencing a generation of physicists and paving the way for further developments in the field.
Albert Einstein's contribution to the old quantum theory came in 1905, when he extended Planck's idea of quantization to light itself. In his paper on the photoelectric effect, Einstein proposed that light consists of discrete packets of energy called photons.
Einstein's photon theory explained the photoelectric effect, a phenomenon where light shining on a metal surface ejects electrons from the material. Classical wave theory could not account for the fact that the energy of ejected electrons depended on the frequency of the incident light, not its intensity. Einstein proposed that each photon has an energy, E equals sign h nu, and only photons with enough energy could eject electrons.
Einstein's work was pivotal in establishing the wave-particle duality of light, a concept that became central to quantum theory. His insights earned him the Nobel Prize in Physics in 1921. Einstein's work on photons provided a new way of understanding electromagnetic radiation, challenging classical concepts and opening new avenues of research in quantum physics.
In 1913, Niels Bohr introduced a new model of the atom that incorporated quantum ideas to explain atomic spectra. Bohr proposed that electrons orbit the nucleus in discrete energy levels and that these orbits are quantized.
Bohr's model suggested that electrons could only occupy certain allowed orbits, each corresponding to a specific energy level. When an electron transitions between these levels, it emits or absorbs a photon with energy equal to the difference between the initial and final energy levels, equal sign num. This explained the discrete spectral lines observed in atomic spectra.
It also introduced the idea of quantized angular momentum, where the angular momentum of an electron in a given orbit is an integer multiple of h bar, reduced Planck's constant. However, Bohr's model had its limitations. It could not accurately predict the spectra of atoms with more than one electron, and failed to explain the fine structure of spectral lines. Despite these shortcomings, Bohr's work was crucial in advancing quantum theory, laying the groundwork for future developments.
Arnold Sommerfeld extended Bohr's atomic model by introducing elliptical orbits and additional quantum numbers.
So in 1916, Sommerfeld proposed that electrons could move in elliptical as well as circular orbits around the nucleus.
Exactly. This refinement aimed to address some of the limitations of Bohr's model, providing a more accurate description of atomic spectra. Sommerfeld's model included two new quantum numbers, the azimuthal quantum number and the magnetic quantum number. These additions helped explain the fine structure of spectral lines observed as small splittings in the spectral lines of atoms. By incorporating these new quantum numbers, Sommerfeld's model provided a better fit to the experimental data for the hydrogen atom and partially addressed the spectral lines of more complex atoms. Sommerfeld's contributions were significant in advancing the old quantum theory, offering a more detailed and nuanced model of the atom. In 1924, Louis de Broglie introduced a groundbreaking idea that extended the wave-particle duality of light to matter. De Broglie proposed that particles, such as electrons, exhibit wave-like properties. He suggested that a particle with momentum is associated with a wave of wavelength lambda. De Broglie's hypothesis was revolutionary, challenging the classical notion of particles as point-like objects. This idea provided a new perspective on the quantum condition, suggesting that the allowed orbits of electrons in an atom correspond to standing waves. According to de Broglie, the circumference of an electron's orbit must be an integer multiple of its wavelength. De Broglie's hypothesis was quickly embraced by the physics community and formed the basis for the development of wave mechanics. It provided a crucial link between the old quantum theory and the emerging wave-based descriptions of quantum phenomena.
Hendrik Kramers contributed to the development of the old quantum theory by introducing the concept of a transition matrix. In the early 1920s, Kramers proposed that the probability of an electron transitioning between different energy levels could be described using a matrix.
Kramers analyzed the classical motion of an electron in an atom and expressed it as a Fourier series. He then postulated that each term in the Fourier series corresponded to a possible transition between energy levels, with the amplitude of each term related to the transition probability. This approach provided a way to connect classical periodic motions with quantum transitions.
Werner Heisenberg, Max Born, and Pascual Jordan later formalized this approach, using matrices to describe quantum operators. Kramers' work highlighted the importance of mathematical tools in understanding quantum phenomena. His transition matrix can be seen as a precursor to the matrices used in matrix mechanics, providing a stepping stone towards a more complete quantum theory.
The old quantum theory introduced several key concepts that became central to quantum mechanics. One of the most important was energy quantization, the idea that energy exists in discrete packets rather than as a continuous spectrum.
Energy quantization explained phenomena such as blackbody radiation and atomic spectra, which classical physics could not account for. It suggested that the energy levels of atoms and molecules are quantized, with electrons occupying specific energy states.
Another crucial concept was wave-particle duality, the idea that particles can exhibit both wave-like and particle-like properties. This concept was initially proposed by Einstein for light, and later extended to matter by Louis de Broglie. It suggested that particles such as electrons could be described as waves, with their wave properties influencing their behavior at the atomic level. These concepts were fundamental in shifting the understanding of atomic and subatomic processes.
Despite its successes, the old quantum theory had significant limitations. It couldn't accurately describe systems with more than one electron, like helium.
The theory relied heavily on classical mechanics, using quantum ideas in an ad hoc manner. Classical concepts like trajectories and orbits were inadequate for atomic particles. It couldn't explain spectral line intensities or fine structure in spectroscopy. The old quantum theory played a crucial role in the development of modern quantum mechanics.